All right, let's try another one. So in this example, we're given the graph of function f of t, and this function represents the population of the United States t years after the beginning of year 1800. All right, so here's our graph, and this is our curve f of t. And what are the units for this vertical axis? So, considering in 1860 there weren't 30 people in the U.S., what are the units here for our vertical axis? And millions of people. All right. So, and what about for the horizontal axis, t? That represents t. So that's time, or specifically in this case, years. And it's years after 1800. So like 0 would mean 1800. 10 would mean 1810. 20 would mean 1820, and so on. All right, so for this problem, we're going to look at a few different calculations here. And in part 1, we want to find the average rate of change, or average rate of growth, of the U.S. population from the year 1840 to 1870. All right, so we want the average rate of change. What's the average rate of growth of this population over that interval of time? So we know our average rate of change formula is what is it? Well, we have we have our interval here. So in this case, it's going to be f of 70 minus f of 40 divided by 70 minus 40. So this is our rate of change, average rate of change formula. It's the difference quotient that we've been looking at. Now, why are we using 70 and 40 here? Well, that's because our time units, 70 represents the year 1870, and 40 represents the year 1840. And that's because we're counting how many years, starting at 1800, how many years are we at? So, for instance, for 1870, that's 70 years beyond 1800. So that would be t equals 70. All right, so let's actually calculate this value here. And we need to look these function values up on our graph. So at 40, let's draw in our point. Looks to be right around there on our graph. And this is going to be an estimate. So we're just using our graph to kind of determine the function values, and in the end it's an estimate. So I would say this looks to be about, maybe it has the coordinates 40, maybe the y coordinate is, or the vertical coordinate is 17. We're just estimating. And then for 70, that point looks to be right around here, and maybe that's 40? Maybe 41? What do we want to call it? Let's call it 40. So I might call this as 70, 40. So again, we're just estimating based off of what this graph looks like. All right, so the y coordinate in each of these is the function value. So when we go to our difference quotient here, f of 70 then is going to actually be this number right here. So this here is the function value at time 70. And then what's the function value at time 40? Well, that's this value right here. So this is f of 40. So we're just looking at the y coordinates for our points. So 17 we said. And then we do the 70 minus 40 down there, we get 30. And 23 over 30 is our fraction here, which ends up being approximately 0.77. So this is, in the end, when we're calculating this average rate of change using a graph, it's an estimation, because you could argue this maybe was 41. Maybe this is 16. Maybe it's 16.5. So we're just kind of estimating these as best as we can. All right, so this average rate of change is 0.77. And the kind of the important thing to kind of keep track of here are what are the units going to be. And it turns out for rate of change, it's the units along the vertical axis divided by the units along the horizontal axis. So in this case, millions of people per year. So on average, during these 3 decades, during this time interval, the population was growing on average 0.77 million people per year. And we know it's kind of hidden in the wording here, average rate of growth. We know that the population was growing because this value is positive. If this value is negative, then the population would have been shrinking. So the average rate of growth, the average rate of change, is approximately 0.77 millions of people per year. And it's growing because the value is positive. All right. Try another part. Let's see what else we could investigate here. So for part 2, how fast is the population growing in 1840? So this wants to know not the average rate of growth over some time interval. We want to know how fast the population was growing exactly in the year 1840. So this is the instantaneous rate of change. And we know that this is the limit of our difference quotient, but it's really the derivative. So this is actually the derivative, and we're going to plug in 40 because of 1840 here. So we're going to plug in the appropriate time value. Remember, we're measuring time in years after 1800, and then our vertical axis is in millions of people. So we want to know how fast the population is growing in the year 1840. So that's an instantaneous rate of change. And so it's equal to the derivative where we plug in our appropriate time value here. Now, the issue is we don't have a nice function that actually gives us this curve. We just have the curve to work with here. We just have this graph to work with. So how do we actually calculate this derivative? Well, we identify the point at time 40, call that point P. We said it looked to be about 40, 17. We draw in the tangent line at that point. So again, draw in the tangent line as best as you can. And, this, I have it kind of drawn in already, but you would actually draw this out for yourself. So that looks pretty good. And then what we want to do is we want to, in order to really estimate this derivative, we have to estimate what the slope of this tangent line is. So we have our function f of t here, and then we have our tangent line at x equals 40. And we really need the slope of this tangent line. All right, so how are we going to get that? Well, this is where we look at the change in y over the change in x. So in order to figure out the slope of a line, we need 2 points. So we have our point of tangency here, and then just pick a second point. So we have all these different points to choose from. Try to pick an easy one. So pick something that's, goes through a grid line. So if I were to kind of use one, maybe like this one. Looks to be about has coordinates 60, what do we say here? Maybe 60 comma 27 if we're looking at this. So it's, here's 20, here's 30, looks a little closer to 30, maybe 27. We're just estimating. So use the graph as best as you can. And then we want the slope of this line connecting those 2 points. So it's just the change in y over the change in x. So what's the change in y? Well, that would be 27 minus 17. And what's the change in x? It'd be 60 minus 40. So it looks to be about 10 divided by 20, and this is really an approximation here. We should be clear. So, we're approximating a whole bunch of times here. We're approximating when we identify the coordinates. For this point, we're approximating when we identify the coordinates for this point as well. So the slope of the tangent line is going to be approximately this fraction. And that ends up being 0.5. And so in the year 1840, what this value represents is how fast the population was growing in the year 1840. So it's growing at a rate of about 0.5 millions of people, so about 500,000 people per year. And we know it's growing, the population is growing, again, because this value is positive. If this value were negative, then the population would be shrinking. All right. So instantaneous rate of change, how fast the population was growing at a specific moment in time, that's the derivative, that's the slope of the tangent line. We also looked at the average rate of change over a given time interval. So really this is kind of like graphically, or if we're thinking of it, be kind of like the slope of a secant line. That's really what we're doing there. Slope of a secant line that intersects the curve twice. And let's just try one more for comparison purposes here. Let's decide, was the population growing faster in the year 1810 or 1860? So again, 1810 would correspond to t equals 10, and 1860 would correspond to the time value 60. And so what we do is we want to determine the instantaneous rate of change in the year 1810. So we would plot the point there, which looks to be, well, right around here. And then we draw in the tangent line. So this is our tangent at t equals 10. And then we're also interested in the year 1860. So find t equals 60 along the horizontal, plot the point on the graph, and then sketch in what you think the tangent line should be. So again, this tangent line is an estimate. So you're kind of drawing in what you think the estimate should be. And you're estimating what the tangent line should look like. Oh, that was another place. Going back to part 2 here. We estimated when we picked these coordinates. We said, yeah, that looked about 27. That looked about 17. But we also estimated when we actually drew in this line. So there's a whole bunch of estimating going on here. But, reasonable estimating. So this does actually look like what the tangent line would be. And that these coordinates are fairly close to what the actual values might be as well. So a lot of estimating here, but we can kind of conceptually understand what's going on here. So we're interested in the rate of change at t equals 10. We're interested in the rate of change at t equals 60. So we've plotted those 2 points, drawn in the tangent lines. And what we can see is that the slope of the tangent line, this tangent line here at t equals 60, is steeper. So what that means is our rate of change at that moment in time is more. It's growing at a faster rate. Our population is growing at a faster rate here because the slope of the tangent line is greater. So since the tangent line is steeper at t equals 60, the population is growing faster at that year. So this steeper tangent line means it has a larger slope, larger positive slope. It's pointing up, which means the growth of the population, the instantaneous rate of change here, must be larger than the instant rate of change for this other tangent line, which is, flatter. Still going up, but it's not as steep. So the slope would not be as large. So the fact that this slope is larger means that the rate of growth is going to be faster or larger as well. All right. So just a little practice being able to kind of calculate and interpret, given the graph of a function, average rate of change, instantaneous rate of change, and then just also being able to kind of keep track of units. All right. That'll do it for this example.